Hello and welcome again to this lecture on the design of power transmission systems. What we will focus on today is the issue of gear selection. How to select the number of teeth on a gear, how to select the appropriate working conditions for the gears, and how to determine the way that they mesh together and the gear to gear ratio, and then how you can convert power to torque and so forth. So all of these issues, when we have like powertrain and a train of gears, how do we make all of these selections and use it in actual design? Also, we would like to know, when we have gears meshing together, there's going to be power converted into a torque or force, and the forces will be reacted on the shafts themselves, and therefore we need to understand how to do proper force analysis for the gears before we can design them. And in fact, the main concept in selection for the number of teeth on a gear related to how the conjugate action takes place. We talked about conjugate action between two teeth, and that the conjugate action is necessary to transfer the power or the force normal to the mating surfaces. If conjugate action is not guaranteed, then the force cannot be transmitted normal to the two surfaces, and you would have excessive wear on the teeth of the gears themselves. So in order for us to select the minimum number of teeth in a gear, we must look at the idea of interference. And interference is when we have a driver gear like this one, and the tooth is made by the involute process, and a driven gear tooth such as that, and they have a contact point as in here. So if it turns out to be that we have perfect conjugate action, then the forces will be normal to the surfaces. However, if you look carefully at these two mating gears, you will see that the contact from the driver gear is on the flank side, and the tip of the tooth of the driven gear is making the contact before conjugate action is achieved. So this process here is not very good for the lifetime of the gears, and must be reduced. And this is the way that we would like to remove this kind of interference. To not to allow for the interference, we could do it two ways. One way is we can go back and reform the gears, cut them by a process called undercutting, so we can shave off some parts of the tooth that is causing the interference, and that is not very good solution. Or the other solution is to actually select properly the number of teeth, the minimum number of teeth. As we increase the number of teeth in the on a gear, then interference will not occur. From geometry, it can be shown that the pinion would have a minimum number of teeth required if the pinion is driving a 1-to-1 gear ratio. The minimum number of teeth required is given by this equation, and it depends obviously on the pressure angle phi in here, and K is equal to 1 for full depth and equal to 0.8 for a stub teeth. However, if we have a pinion that is different from the gear, and we have a gear ratio of the number of teeth of the gear divided by the number of teeth of the pinion to be m, then this equation is generalized to equation 1311, and therefore if we just input K equals 1, let's say, and m equals any number that we have, let's say the gear ratio is 6, then we would substitute here with the gear ratio and with K in this equation, and what is left is phi. So phi, as we mentioned, that it could be 25 degrees or 20 degrees, depending on the type of gear that we selected. So in your design, you're going to select the minimum number of teeth, and that is determined by the pinion. Once the pinion minimum number of teeth are determined from the consideration of interference, through understanding of the gear ratio, we can determine the number of teeth required, or the maximum number of teeth required for the driven gear or the gear itself, N sub G. So N sub G for the spur gears, that is largest gear, and once we specify the pinion number of teeth, we can determine the number of teeth for the gear itself, knowing the minimum number of teeth for the pinion that we have selected already and the pressure angle. So we would use equation 1312 to determine the largest, the number of teeth and the largest gear. In case we have a pinion and a rack, the number of teeth in the rack is essentially infinite, so we can still determine the number of teeth on the pinion by using the same kind of argument here. And the argument is that we would have, in this case, we can apply equation 311 with m is equal to infinity. So if you take m equals infinity and you take the limits, then you'll see that the result of that is going to be we will have the number of teeth on a pinion that is in contact with a rack is 2k over sine squared phi, and that would give us the required smallest pinion to drive a rack. Okay, so if you use these equations, you can actually very easily program them on your calculator or using MATLAB. However, we have tables also to look up to determine the minimum number of teeth required for the pinion. So if you look at the table here for a 20-degree pressure angle, then the equation gives us that if we have the gear ratio, depending on the gear ratio here, then the minimum number of teeth, let's say if it turns out to be 13, then the corresponding maximum number of teeth on the large gear is 16.45, and we can round that off to 16, and that gives us the maximum possible gear ratio for that particular number of teeth. Of course, if the pinion has more teeth, like 17, then you can get to a very high gear ratio of 77, and the large gear can have an enormous number of teeth, as you can see here, 1309. So these are considerations that are used to determine the minimum number of teeth, and correspondingly, if the pressure angle is changed to 25, you can look up this table, or you can use the previous equations to determine the number of teeth required. So if I go back to the equations, which will be here, so in this equation, you have decided already on what is given is, if you look at here, given m is the gear ratio. So you want to have a speed reducer, and the speed reducer, you want to reduce the speed by a factor of 10. So m is the gear ratio, would be the ratio of the number of teeth on the gear divided by the number of teeth on the pinion. That's 10. So you input 10. However, if you want to reduce the speed by a factor of 100, then you'll be out of luck, because that will be such a large reduction that you will not be able to use it to use one stage gearing system to achieve that. So we're going to discuss this issue in a few minutes, as soon as we understand now the selection process for the minimum number of teeth required for a two-stage gear train. So if m is equal to 10 given, Then we want to find and we have also phi equals 25 degrees. Then we want to find n sub p. Once we find n sub p, then we can find, now the next thing is to find n sub g, and that determines both the n sub p and n sub g and the final gear ratio that is achieved. And that's essentially what's happening here, is given let's say a gear ratio, this is given here, once we and the angle is given, then we will find that if we apply the equation, we find n sub p equals 15, and then we find n sub g equals 45, and in integer numbers it will be just 45, as you can see here. Okay, so up to now we have a good idea about how to select the number of gears, the number of teeth on a gear, and how to find the proper gear ratio. As we mentioned earlier, now one of the objectives is to reduce speed, as you'll see in the design project that we will assign. So in the design project, we will have an input RPM, and we want to have an output shaft that has a much lower RPM. In this case, if the shaft layout, it turned out to be all axes are parallel to one another, we are in good shape, because we can use spur gears all the way through. However, or we can also use helical gears, which transfer some force in the axial direction that we can take up by the bearings of like thrust bearings on the ends of the shaft. However, if we want to transmit power from one axis to an axis that is normal to that, perpendicular, we have a choice to use a straight bevel gear, or we can use a worm gear. So instead of just going through all of the different gearing systems, we decided to explain the variation from a spur gear parallel axes to a bevel gear for intersecting axes, and we'll give a couple of examples on how to compute the force systems on these gears. So the bevel gears, straight bevel gears, is, as you can see from here, where we are transmitting power from one axis to an intersecting axis, like here. And in this case, what is important about the straight bevel gears is to remember that the teeth themselves are lying at an angle for the driven gear, and this angle is called capital gamma. So this is cap gamma. And the driver gear is at an angle that is also lowercase gamma. So this is the bevel angle, which does not exist in the case of spur gears. So if you imagine the teeth here are located on a circle, and the circle is just going around like this on a cone. So there's a cone where the teeth are spread on that cone. If you take this circle and you look at the radius, so if we, let's say we're going to look at the radius from the center of coordinates to the tooth itself. So if we take it from here, from this point, and to the location, the pitch angle, the pitch circle on the tooth of the driven gear. This is the profile. This is the involute profile that goes with it. And now if we take this tooth and look at the circle here, then the circle has a radius, a cone radius of r sub b. This is the base radius for that circle. So if you imagine that you kind of project this circle on the horizontal, it would be much bigger, and it has the r sub b, and therefore there's a virtual number of teeth that one can imagine, which is the circumference of the base circle divided by the circular pitch on the bevel-gear, and that gives you a virtual number of teeth that is projected on the horizontal plane. So these are considerations that we would kind of see in our let me see, I just kind of lost that one here. So these are considerations that we will have for bevel gears when we start looking at the force system and how the forces are transmitted in the next section. And for us, if we're using bevel gears, this table shows us the different formulas for the working depth, which is 2 times 1 over P, which is 2 times M. M is the module, so you have the working depth is 2 times the module. The clearance, instead of a quarter, it becomes 0.188 over P plus 0.02 of an inch. And then we have various correlations for the addendum of the gear, the phase value, the gear ratio, and the minimum number of teeth are specified. So for any design application, we should be able to use this kind of information. Now what I wanted to do is talk about gear trays. And the idea here is that I have a very high RPM and I want to reduce it to a low RPM, or vice versa. What do I need to do to select the various gear systems? So far we've learned that the minimum number of teeth on a pinion are decided upon by avoiding interference, and we have that already in hand. Now, how do I go from here to designing the entire gear train? And what is a gear train? So the gear train is basically, we have a generalization of a driver pinion and a driven gear. If we have only gear 2, which is a pinion, driving gear 3, which is the driven gear. In this case, the gear train has only one stage, so it's a one-stage gear train. And the idea here, as we learned before, is the product of n times n is constant. So if you increase n, this is the RPM, and this is the number of teeth. And the reason for this formula is that we know that the linear velocity at the tangent of the 2 gears is fixed, and the linear velocity is r omega. So r omega is fixed, and r is like d over 2, and d over 2 becomes the number of teeth via the pitch, and omega is like the RPM, which is n. So it turns out to be, so this is constant, turns out to be that the tangential velocity on the tangent between 2 gears is constant, and therefore the product of the RPM and the number of teeth will be constant when we have any contacting gears. So if we have a 2-stage process, 2-stage gear process, then N3 will be equal to capital N2 over N3, this is the gear ratio, times the RPM of the driver itself. So this is driven is equal to RPM of the driver times the gear ratio. Now what happens when we have a real gear train like this? So if you look at this, we have a pinion that has a number of teeth N2, and it is rotating at an RPM lowercase n2, and it's driving a driver. It's a driven gear with a number of teeth n3 and rotating at lowercase n3. And then this gear, the third gear, is meshing with fourth gear, but the fourth gear here is on a common axis with a fifth gear. So the fifth gear does not mesh with the third gear. However, it is on the same common axis as N4. So N4 is actually here is like an idle, like called idler. So it's not really doing much but being driven, and then it rotates gear 5. Gear 5 drives gear 6. So the number of stages is from 2 to 3 is 1, and then from 3 to 4 is 2, and then from 5 to 6 is 3. So 3 stages of that gear train. So the number of stages is odd, and therefore you'd expect that the velocity, the RPM of gear 2, the direction of rotation of gear 2, if you have an odd number of stages, will result in a reversal of the RPM on the output shaft. So that's consideration 1. And therefore, if the number of stages is odd, we get reversal of the direction of rotation. If the number of stages is even, we would get the same direction of rotation of the output in relationship to the input. The second is that we want to find the RPM of the output shaft given the RPM of the input shaft. And from the previous generalization that we have discussed, that n times n is equal to a constant, then we can apply this to every stage, and therefore we get n6. Like if you see, look at this, if I want n6, then I say that n6 times capital N6 is equal to n5 times capital N5, and so on. So in this case, I can get the what is called n6 would be lowercase n6 would be the output would be equal to the input RPM times the product of the driving tooth numbers divided by the product of the driven tooth numbers. So if you look at the driving the gears are 2, so this is driving. 3 is also driving because 3 is driving 4, and then 4 is not driving anything, but 5 is driving 6. So 2, 3, and 5. And the driven, it turns out to be that 3 is also driven, is a driver and driven, because it goes both ways, and 4 is driven, and then finally 6 is driven. So the rule that we have here is that the output, the last RPM and last is equal to the train value. E is a train value, and that is determined by your design, times the final RPM that we have, N final. So this is the way we design for a gear train to transmit the power. Now, in many cases, we will see that we cannot do a reduction in speed directly because the ratio is so high. So we have to break it up into stages. However, because space sometimes is limited, then we use a technique called compound gearing. And in compound gearing, in this case, we have the 2 gears, we put them on the same shaft. So if you look at this intermediate shaft, this is, let's say, an input shaft here with the pinion. So the pinion is very small and it has a small number of teeth. An intermediate shaft, the intermediate shaft has a driven gear, and then it has a driver gear. So the 2 of them are on the same shaft, they rotate with the same speed. Of course, this one is idle, but this one is driving. So we would have, if you look from this projection, the two gears will be on the same shaft, as you can see here, and therefore you can have a transmission. So the direction, you have a system where you're coming input from here and you're going to output from here, and if the input is going this way, then this will go the opposite direction, and then this will go back to the same direction. And the reason is that we have one stage and then a second stage. So this is 1, 2. So the number of stages is even, and therefore the direction of rotation remains in the same direction as the input. So now we have possibilities for doing design. So what I'd like to do is take a couple of examples. The first example that you'll see, we're going to design a gearing system for reducing speed, and we will do that by considering limitations on interference, and also by considering reduction on a number of stages, and that will result in a certain ratio that is required. So we need to design a gearbox, and the gearbox will provide a 30-to-1 increase in speed, but we want to minimize the overall gearbox size. So in this case, we want to specify the appropriate teeth number, so we can actually order such teeth, like in real design projects like the one that we have in a physical class. We actually we order different gears, but we need to know how many teeth on the gear that are required so that we can mesh them together and put them on the shafts and make the gearbox. So because the ratio is greater than 10, it's the 30, and it's less than 100, then we can do a two-stage compound gear. So to do a two-stage compound gear, we're going to take the gear ratio 30, take the square root to make it approximately even on the two stages. So theoretically, we would have a gear ratio of 5.477 on each stage. But this we will have to do a little bit of more accurate calculations once we consider the pressure angle. So if you consider the pressure angle and this kind of gear ratio and go to the formula that we developed for to avoid the interference, then we find that we need 16 teeth on the gear. And therefore, we can say that the number of teeth for the mating gear is 16 times this theoretical value of the gear ratio, square root of 30. That gives me 87.64. Then we go back and we say we can't find really a gear with 87.64. Then we choose a gear with 88 teeth, and therefore we have a two-stage gear train. The first stage has a gear ratio of 88/16. The second will have the same, and therefore the product will give us the train value. The train value is 30.25, and that is kind of close enough to the requirements, is within 1% tolerance. So we really, we did the design, but we are within the 1% tolerance. Now we can ask yourselves, what happens if I want to insist to make like an exact 30-to-1 increase in the speed? The solution is that to make the train value equals 30 exactly, start from there and divide it, instead of 5.7 something, then we divide it into 6 times 5. It's easy. So we don't have to have the same gear ratio on the two stages. So from 2 to 3, you go up by 6. From 4 to 5, you go up by 5. So that's the increase in the speed, and the stage 1 is a little bit more than the increase in the speed in stage 2. So we have 2 equations and 4 unknowns. We have n, 2, 3, 4, 5. And therefore, we need some other constraints. We can select any number of combinations that are required. So one constraint we know about is that we want to prevent interference, and usually you prevent interference for the smallest number of teeth on the first pinion. So we will just select now, assuming a pressure angle of 20. It gives us the minimum number of teeth will be 16 on N3. This is the smallest. So if this is 16, you multiply this by 6, you get N2, and therefore we can determine the number of teeth in each stage. So 6 times 16 gives you 96, and then we also select 16 for the second stage as the minimum number of teeth to prevent interference. We get 80, and the final train value, overall train value, remains to be exactly 30 as required. Now there's another design that can be very important in power transmission, and that's called the compound reverted shaft design. So we have an input shaft, and I want it to be exactly in line with the output shaft. That's a reverted design. So if I have a rotation very high speed here, then this can go very slow. How do I go from very high speed to very slow speed? Then I must need an intermediate shaft, and my design would look like this. So the input would be here, would be 2. This is gear 2, and then the intermediate would be shaft gear 3 and gear 4. These are intermediate, and the output would be gear 5. So the requirements that we have is that we must have the diameter of 2 plus the diameter of 3 equal the diameter of 4 plus the diameter of 5. Otherwise, the two axes are not going to be aligned, or the input and output is not going to be aligned. Which means that if the diameters are equal, like the sum of these two equals sum of these two, and the diameter is proportional to the number of teeth because the pitch is constant, so the diameter and the number of teeth are proportional, then we can replace diameter relationships with number of teeth relationships because the pitch is constant. So we have one equation and 4 unknowns. N2, N3, N4, and 5 are unknown, and we want to determine those for a given application. So let's kind of take an example on this. So we want to have a gearbox, and we want to have an exact 30-to-1 ratio. So this is one additional piece of information to increase the speed, and we want the input and output shafts to be in line. So it's a reverted shaft design. So in this case, a 30-to-1 ratio, we're going to achieve it with 2 stages, as we mentioned before. First stage is gear ratio of 6. Second stage is gear ratio of 5. And now, because it's a reverted shaft design, then N2 plus N3 is equal to N4 plus N5. The last piece of information is that N3 should have a minimum number of teeth of 16 as a result of avoiding interference. So we have 1 condition, 2 conditions, 3 conditions, and 4 conditions to be solved in 4 unknowns. And that's easy because we can start from N3 being 16. We can get N2, and then N2 and N3 will be the sum 112, gives me N4 plus N5. And then because I know that the gear ratio for stage 2 is 5, then we are able to solve exactly for the number of teeth on gear number 5. So if you look for this design, you find that one issue that we discovered is the number of teeth on the 5th gear are actually not integer. And that's kind of a constraint that we must have. We have to have an integer number of teeth. So what can I do is go back, and instead of having, we know that the number of teeth N3, a minimum is equal to 16 from the interference, but it could be larger than 16. So we could go back and change this to 17 and redo all of the calculations, 18, redo all the calculations, and so on. Or we can do it a little bit more intelligently by assuming that n3 is equal to 1, just an assumption here equals to 1, do all the calculations for just n3 equals 1, and then readjust so that we can have all of the number of teeth to be integer in this form. And that's what we'll do here. So if you look here at the solution that we have n3 is assumed to be 1, so n2 is 6 times, and then n2 plus n3 will be 7, and this will be equal to n4 plus n5. And since we know the gear ratio for the second stage to be 5, then we can find n5. So n5 turned out to be 7, 6. So in order for us to get n5 to be exactly 7, we have to multiply by 6. And therefore, if we multiply everything by 6, then our system will have integer number of teeth on every gear that we have designed. And that's exactly what we did here. So we go back now and we have 6. So if you go here, if you have n5 times 6, it gives you 7 teeth basically for n5, and for n2 we will get 6 times. So we'll have n2 will be 6 times n3, and n3 will be 18, and then we proceed with the solution to find all of the number of teeth in the system. One thing that I forgot to mention, that n5 itself, we know that it must be 7, right, or multiple of 7. But we have another constraint, that this number here, if we just use 7 teeth, it will not satisfy the constraint of interference, and therefore we have to increase that by a multiple. Let's say 2 times or 3 times or 4 times. 2 times it gives 14, which is still below the minimum, and therefore we multiply by 3, we get 21, and once we get 21, then the problem is totally solved, and we have designed the entire gear train in this case. So I think that covers the ideas of gear trains and gear designing for the proper number of teeth, and also for the entire gear train if we wanted to design that system. And the next we will talk about force analysis in the next segment.